Thanks. Cool. All right. Hey, everyone. So I'm Rebecca. I work as a team lead for a couple of the data science teams at Shopify. My talk is kind of on how not to overfit predictive models. It kind of started as that and then has morphed a little bit. We're still going to cover a lot of the key concepts. It's kind of more like building your models for resiliency when they're in production, or like if someone were to really it's more accurately like if someone were to adversarially kind of try and mess with your data. What are some strategies for making your models more resilient? But we'll see what you think as we go through. Cool. Oh, no. There we go. So a little bit about me. So I used to be a pure mathematician, and then like 5 years ago, got out of that business and kind of never looked back. So I've been at Shopify for the past 2 years. It's been a really great experience. Still pretty new to the Python community. First time at PyCon, but really excited to be here. So really quick overview, we're going to try and get through a lot in like 10 minutes. So bear with me, and also if you have questions after, we can chat. So one of my kind of rationale is often when you're pushing models to production, things change quickly and kind of out of your control. And as nice as it would be to retrain your model every time there's like slight variations or changes in your data set, oftentimes you want to spend your time building cool new models and not working on like maintaining constantly the models that you have running. So really kind of some principles around like making sure your models have like a good, robust fit before you push them in production. And then also like some strategies for resiliency and my kind of take on using Ensemble Models to do that. Hopefully we'll be like kind of open to everyone, but if you have questions after, we can chat. So things we're gonna cover, goodness of fit, Ensemble Models, and why these are good things in like 8 minutes. Whew. So how do I know if my model is well fit? So kind of the like standard overfit diagram, you can see here like the black curve. It's a lovely fit, what we would want from our models. Green curve, overfitting, you're modeling noise, not the actual signal from your data set. So what this means is you have like a good, robust prediction that as you feed it new data points or new training data, your model performance continues to stay fairly stable over time. If your model's been overfit, likely what will happen is you'll push your model to production and you might have like a few good couple days of lovely performance, and then it's going to start degrading over time, and you're going to have to constantly be in this like retraining cycle. So a couple other things, usually one thing I'll talk about is like benchmarking your data set. So you should have some expectation of how your model should perform or what like accuracy is expected when you start building your model. I usually like to use like a really simplistic model right off the bat, use that to generate kind of like a baseline performance, and then go from there. Yeah, so moving on, what I did, or kind of like my really simplistic, hacky way of representing this is I took one of the kind of like base data sets that's loaded with sklearn. So this is the UCI wine data. You're trying to classify wine based on these characteristics. So wine is either class 1, 2, or 3. Anyone can use this data. It's like readily available, so like you can go home and hack with it. And what I did is basically just added an additional bad training variable that would make this like very simplistic but easy to recognize as we go through. So what did I do to our data? I should be clear as well, this is not like a normal process when I'm like building predictive models. Please don't, a takeaway should not be go home and add like a bunch of noise to your data. What I did was take like our variable class as our target predictor and just added like a random like uniformly distributed like number between 0 and 1 in order to create this like noisy variable. And so that's gonna be affiliated with about 80% of the records in our training data set. 20% of our data set has these just like random numbers between 0 and 1. So for 80% of our data, we have this really like highly correlated thing that's going to be super predictive in our training data set. 20%, it's just nonsense. And then we have a couple test data sets as we go through that like percentage shifts over time to kind of represent how our data has changed. So it goes from like 20% to 50% to eventually be 100% of our data just has this like, it's purely just like a noise column that's added in. And what we'll see is like training the data on this means that over time, like our model just starts sucking. So I did like a quick visualization just to show like that representation of how important this variable is in our training data set and how it is in our test data set, just using Seaborn. This is like a pretty standard step when you're doing predictive modeling. You just want to look at the contrast isn't so great up here, but bad variable, as it's so aptly named, is really highly correlated with our target class in 1, so like dark red, high correlation. It's right around like 0 in our test data set. So what's going to happen is our model is going to go really hard on saying bad variable is the best thing. We can predict everything with this. And then later on, it's going to just not know what to do with itself. All right, so again, just a really simplistic benchmark. All of the examples in here are pretty like low level, just like the most simplistic models. You don't need to do like crazy things in order to create like a good example of ensembles either. So I just did a decision tree and benchmark what our accuracy score would be. So we're getting about 92.5% when we don't have this noise variable, and we're not doing anything like fancy or magical, just like some baseline cleaning and transformations. So what happens next is, so we use kind of a similar transformation step, so everything has kind of been kept the same, just we have this like additional noise variable that's been brought in. And so what happens is our model score on like our first test data set, which is like this 80-20 split, is great. We're getting like 97% accuracy. We're super happy. And then it goes to 50-50, and we go down to 86%. So we have a 10% drop in accuracy just by like 1 level of change in our data for 1 variable. And I actually was like experimenting with a bit. When you get down to like 100%, this goes down to like 33%. So you're just like randomly guessing what type of class of 1 it is. So how can we fix this? So some things, like obviously in this case, feature selection would be very important. Like don't bring noise variables into your model. But I think like proper data prep is a really important step in that. Cross-validation, so similar exercise, did like a 10-fold. You choose like k-1 samples, have like 1 test sample. Use the scores across that to see if you have any like over-indexing parameters. That's like a good way to deal with this as well. Getting a more robust data sample, like if we continue to sample this over time, it would be much better. I'm going to go past all of those and talk about ensemble models really quickly. So what's an ensemble model? So 3 main types I'm going to cover. Whew, this is a lot in 10 minutes. Sorry if I'm going really fast. So bagging, boosting, and stacking. The like TLDR of ensemble models is we're just taking a bunch of models and combining them together in order to get one model that's more robust and has like a larger variety of information and techniques used to derive those scores. So bagging, we're using training data, like a bunch of different subsets, and training classifiers, or I guess regressions with them, and then using average or majority voting to derive like what our prediction is going to be. Boosting, we're usually working sequentially, so we're training one model after another, and we also weight like incorrect predictions, so we're like usually getting better over time. That stops with like an arbitrary threshold or when accuracy starts to decline. And then stacking is when we have like a bunch of models and then we use another model to bring them all together. Whew. Oh man, so fast. Okay, so what happens when we do this? So I just went through and did some like fun and said like, okay, what happens if I take a random sampling of features and a random sampling of the data and just do this with like 4 different models and then bring them all together? And what happens is we get a larger variance of performance, but if we do like just like an average kind of weighted, just like an unweighted average to bring them all together, our performance drops to 92%, but on the test data, we actually get like variance of 2 to 3 percentage points over time, which is really cool because we still have noisy data and like we didn't really do anything interesting, but our model performance got better and was more stable. So when should I not do this? Whew, okay. So in place of doing proper data prep and cleaning, ensembles are great, and I actually think it's a really good way to build resiliency and like make your models more robust. But don't do that instead of like actually taking the time and going through your data. If the cost is very high, they take like a long time to run and it reduces explainability. And if your ensemble is overfitting, which means you probably need to do more data prep and cleaning. Thank you. Whew.